Hi, June. Okay, good. Close this door. Okay, I'm back. Hi, David. Hi, Michael.
Morning.
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 Okay, let's see. Can you hear me well?
Yes. Yes.
Okay, let me test. Hello. Sound better with this microphone on? Or about the same?
They're pretty similar.
Okay, very similar. Okay. Well, I was told to buy a mic. Maybe I'll buy a mic for the lecture, then my voice will come across better. Let's get started then. Do you have any questions before we get started? If not, today I'd like to talk about cavity resonators. And it's a pretty interesting topic. And you have come across resonators before as an electrical engineer. And the place where you have come across a resonator is an LC tank circuit, for instance. When you have an LC tank circuit, there would be certain frequencies at which I guess you have learned this from your undergraduate day. If the frequency is 1 over the square root of omega, square root of L times C, then the resonator can resonate. The characteristic of a resonator is that it does not require an external driving source. For instance, if you think of this as a circuit thing, you don't need an external driving source to get the current going back and forth. There will be current going back and forth between the capacitor and the inductor due to the exchange of magnetic energy stored and electric energy stored, but you don't need an external driving source to make that happen. The energy just goes back and forth by itself. Okay, what are resonators good for? You probably have seen that in your undergraduate day. If you have a voltage source, okay, and if you want to transfer this to a load, let me call this a Z load. You can transfer the energy from the voltage to the load this way, but if you want to preferentially transfer only a certain frequency, you can put an LC tank circuit in parallel. And when the frequency is hitting the resonance frequency of the LC tank circuit, this becomes an open circuit. And the transfer of energy is perfect. However, at other frequencies, then the LC tank circuit acts like a shunt impedance. Okay, you know that when an LC tank circuit is at resonance, its impedance is infinite. Away from resonance, its impedance is not infinite, so it can be acting like a short circuit or a shunt impedance to actually not allow all the energy to be transferred to the load. Okay, so this is a very rudimentary kind of a filter. So you can use LC tank circuit as a filter. And how do we make a resonator out of all the things that we have known now? We can start with the simplest resonator we can make from a transmission line. Just take this figure over here. If I were to have, this is not a source now, this is impedance of the source, and this is the impedance of the load. And imagine a wave bouncing back and forth between the two ends. And imagine that these loads are lossless so that they don't absorb energy. Then the wave can bounce back and forth forever, giving rise to a resonant condition, very much like the energy in the resonator, the LC tank circuit going back and forth between the inductor and the capacitor. But this is the energy bouncing back and forth inside a transmission line waveguide. Okay, so how can we use transmission line model to study this problem? We can use the transmission line model by using the transverse resonance condition. Just a reminder, we now know that many things can be modeled as a transmission line. We have seen that when you have, say, a rectangular waveguide, you can actually model a rectangular waveguide as a transmission line as well as sections of transmission line. Even if you have a circular waveguide, you can model it as a section of transmission line by exploiting mathematical homomorphism. Okay, so you can have cylindrical waveguides of any cross section or even microstrip lines. If you have a microstrip line, such as this one, say if you make a microstrip line on top of a substrate, let me draw the substrate this way. And then usually you have this thing sitting on a substrate, and then there's a ground plane below. Let's assume that this is the ground plane. Okay, a ground plane. And you can also think of a microstrip line with a quasi TEM mode as a transmission line. And you can think of that can be becoming a resonator when you terminate a transmission line with two impedances. Well, what is the theory behind this? The theory behind this is that for resonance to occur, you need resonance condition. And we can easily use the transverse resonance condition to derive the resonance condition, very much like we use that to derive the wave guidance condition. We said that a solution may exist in this transmission line if after the wave has bounced back and forth from the two ends, and then after it has traversed the length of the transmission line with this phase factor. Okay, so this transverse resonance condition is very much like what you have learned before, where gamma L and gamma S are the reflection coefficients at these two ends. This end we will have gamma L, this end we will have gamma S. Those are the two reflection coefficients, and then the wave is assuming to propagate back and forth with a phase velocity related to beta Z. Okay? So you can intuitively write down as the resonance condition for this wave to sustain itself without being canceled out. So this wave will bounce back and forth and interfere constructively within this section of the waveguide, and this solution can exist without an external driving source. And when something can exist without an external driving source, like the case of an LC10 circuit, we say that that is the resonance solution. Okay, let's see what the possibilities are. Well, if we have say a short or an open, gamma L is either plus or minus 1. Gamma S is equal to plus or minus 1 for short and open loads. Okay, those you can find very easily. If the transmission line is terminated with other kinds of loads, you know how to find those reflection coefficients too. But then solving this equation would be too difficult. So we just do the simplest case where we have terminated the transmission line with either short or open. Depending on the situation, we can have two cases. One is equal to e to the minus j 2 beta zd is one case. And the other case is when the left-hand side becomes minus 1. There are a few combinations. There are 4 combinations for the product of gamma S times gamma L. So you can have but only 2 equations that comes out. These are the 2 possibilities. Okay, so for the left-hand equation, you can easily solve it. It should be that 2 beta zd is equal to n pi, 2 n pi. Okay, when you require that 2 beta zd is 2 n pi, or beta zd is n pi, where n is an integer, then the resonance condition will be satisfied. However, for the other one, you will have to have 2 beta zd to be n pi, where n is odd. So if you pick 2 beta zd to be n pi where n is odd, then this equation would always be satisfied. So this means that beta zd is n pi over 2, where n is odd. Okay. So you can have different kinds of solutions, and you probably know what the solutions are. You can go back and fill yourself in using a transmission line model. So the solution will look something like that. And for the left-hand side one, which is the one shown here, okay, this one, the wave actually make a full half wavelength from one end of the transmission line to the other end. So if I were to draw this transmission line, the left-hand solution will have solutions where it starts with 0 and it becomes something like that. That's when beta ZD is equal to n pi. And the next one would be something like this. Okay, and then next one would be something like this. But always ending with a 0 at it, two ends. And these are the cases where beta ZD equals n pi. Okay, n is an integer. However, the other case is if you have a transmission line, you don't know what the loads are. The loads will be, maybe one side is short circuit, the other side is open circuit. Then you will have this being -1 on the left-hand side, because if one of this is a short circuit, the other one is an open circuit, you get a minus sign in total. And this equation is the equation that you have finally. And so you have the case where beta ZD is n pi over 2 and odd. And you can actually figure what the voltage pattern should be like. This is actually the current. Okay, I'm actually plotting the current here. Current should be 0 at the two ends, is what you have. And similarly, if you plot the current here, the first mode would be something like current being 0 and then being the maximum near the short circuit. And then the next mode would be something like this, being the maximum near the short circuit. I didn't draw it well, but you know what I mean, okay? And then you can draw the next mode. Okay, always with this ending with an open circuit. No, not ending with the open circuit, ending with the maximum current. The current will be max here, will be 0 here. And if you were to plot the current distribution on this transmission line, you will have all these different modes. This is n is equal to 1, n is equal to 3, and n is equal to 5. Okay, so you can find these resonant modes quite easily. Okay, and that actually we have done before. For instance, we did study this transmission line quite exhaustively. That is when we have a transmission line with a short and an open on the both ends, then you can actually plot the voltage as a function of Z. The voltage should be 0, and then will be maximum at where the thing is open. Then the current would behave the other way around. The current would be the maximum on the left side because it's a short circuit, and then it goes to 0 on the right hand side because it's an open circuit. So you can make resonators quite easily using transmission lines or waveguides, even if the waveguides can be mapped to a transmission line. Are there any questions so far as to how we can make resonators out of transmission line? So the idea is that if you have a transmission line like a coax, this is the case of a coax. Okay, one way you can make a resonator is to short it at the other end with a metal short, and then you just leave this other side open. Okay. However, if you were to make such a transmission line resonator, this is the coax resonator. Okay, if you were to make a transmission line resonator in this manner, The short is very much like a short, like the figure here as shown in this transmission line model. However, the right-hand side, if you were to look at the electromagnetic field on the right-hand side, because of this being open circuited, there will be charges accumulating at the end of the cable, and there will be negative charges at the other end. So there will be fringing field that goes like that, okay, from the outer conductor to the inner conductor. And that depends on the phase of the wave, of course. And this fringing field store electric energy, and that has to be modeled with a capacitance called the fringing field capacitor. Okay, and this stores electric field energy. And so this should be the correct model for this transmission line with an open circuit on one end and a closed circuit at the other end. You probably learned from your take-home exam that solving this problem is not trivial. When this is an open circuit, it's trivial. Well, if you were to put in a capacitor here, you will have some transcendental equations to solve, okay? So one way to solve transcendental equation is to use graphical methods, but I'll leave it for you to play around with if you're interested in finding the resonant frequency of this transmission line. But when this is an open circuit, finding the solution is trivial, okay? So let's look at the case of let me put in a slide in between here. Let me look at the case of a rectangular waveguide. A rectangular waveguide will be something like this, for instance. I can let this side be open, and I can put a short here on this side and see if we can have a wave that bounces back and forth in this waveguide, so that this wave would constructively interfere in such a manner that you can have a solution inside this waveguide without an external driving source, okay? So is this possible? And when this is possible, we can say that using mathematical homomorphism, we can say that this waveguide can be modeled with a transmission line, and the other side is a short circuit. It can be modeled as such, and then the other side has to be an open, and it has to have fringing field capacitor, and this would be the correct model for this rectangular waveguide resonator. However, the beta Z is not simple anymore. The beta Z for this problem would be very simple because this is a TEM mode. Beta Z is just beta, okay? However, for a rectangular waveguide, beta Z is not beta, but beta Z is beta square minus beta S square, okay? And if you recall what beta S square is in a rectangular waveguide, those are the eigenvalues of the problem, or the transverse wave number of the reduced wave equations, and we have solved them previously. Beta S square is m pi over a square plus n pi over b square for the TE MN mode and the TM MN modes. Okay, those are the possible values of betas. And then you can actually find the resonance condition by requiring that beta ZD must be equal to P pi. Okay, P actually is P pi over 2. P is odd integer. Okay, when you choose your P in this manner, you will find that the boundary condition can be satisfied. And then after you have found your beta Z, your beta S is given, you cannot choose to make it different. Then the resonant frequency can be found from this equation. Beta C, beta square must be beta Z square plus beta S square, which is P pi over 2 square plus M pi over A square N pi over B square. Okay. And beta square is omega square mu epsilon. And you notice that there's something different about this formula. This formula cannot be satisfied by all frequencies. Previously, when we have a waveguide problem, we can pick this to be our eigenvalues. Then beta Z could be given by this equation, but beta Z is free to be anything that we choose to have as a wave traveling in a rectangular waveguide. But for the wave to resonate, to have constructive interference when it bounces back and forth, then you can only have this value of beta Z. And when you put in this value of beta Z, this should be a D here, I'm sorry. There should be a D here because you take the D to this side and there should be a D there. And when you put these values in, and if you have already fixed your P, your M, and your N, this equation can only be satisfied at the selected frequency. Those frequencies are called the resonant frequencies of the cavity. Okay, so we can say that this is a resonator cavity. Once you put in the proper termination, of course, we make this an ideal open circuit so that we actually are ignoring the effect of the fringing field, so that beta Z is given by this. If you were to account for the fringing field, this would not be the value of beta ZD, okay? And then the resonant frequency of the cavity, usually called omega M P, MNP, okay, will be given by C. If you take this over to the other side and take a square root, and then P pi over 2D square plus M pi over A square plus N pi over B square, and then taking the square root. This would be the resonant frequency of this rectangular cavity. Are there any questions so far regarding how we find the resonant frequency of a rectangular cavity? So this is very much like the resonant frequency of an LC tank circuit. So at that frequency, you can have a free solution without a driving source. And at these frequencies, inside this cavity or even in the transmission line, you can have a free solution, or also called a natural solution. And these are called a resonant solution. They are given many names: resonant solution or the natural solution. And these solutions can exist without an external driving source. Okay, they exist without an external driving source. Well, this is like the case of solving for, say, a ordinary differential equation, for instance. If I have an ordinary differential equation given by this, say, let me call it beta square yx is equal to 0. This equation has a solution without a driving source. Usually the right-hand side is a driving source. And we learned that in electrical engineering. So when you turn the right-hand side off, this is the solution without a driving source. And when you have an ODE, you're solving a problem without a driving source. Does anybody know the name for this kind of solution? A solution to an ODE without a driving source on the right-hand side. Does anybody know the name for this kind of solution?
Homogeneous?
Very good, homogeneous solution. Okay, homogeneous. So there's a mathematical term for it, homogeneous solution. And the physics term is natural solution. A solution without the driving source. And if you solve this as a boundary value problem where you require the field to be 0 at the two ends, and these are the boundary conditions. Okay, and you will find that this problem has only a non-trivial solution or a natural solution or homogeneous solution for certain selected values of beta. Okay, beta is the wave number. Then you can find that beta, in this case, is 2n pi, n integer. For this particular diagram I have drawn here. And yeah, not beta. Beta L is equal to 2n pi. Okay, L being the length of this resonator, and then beta would be given by 2n pi over L. And this is, if you solve this as a 1D transmission line problem, beta will be omega mu epsilon. And then if you look at this problem then, omega, which is given by C times 2n pi over L, those are the resonant frequencies. Okay, these are the resonant frequency of this 1D resonator. I'm simplifying it to the case of a 1D resonator. Okay. So this is the resonant frequency, and for 3D resonators, this would be the resonant frequency. So it's a lot more complicated, but I hope you catch what I'm trying to say here. So let's go to the case where, do you have any questions before I move on? If you don't have any questions, I would go to the case where beta z equal to 0 or kz equal to 0 case. Because in solving this problem, I'm assuming that beta x, beta y is equal to this, and beta z is equal to this. And I'm not allowing p to be 0. Okay, I'm not allowing p to be 0, but it turns out that you can still have beta z equal to 0 in this equation. For instance, I can put p equal to 0 here and still solve these equations, okay? Before we proceed, let's look at these equations again. These equations correspond to TE and TM modes bouncing back and forth between the two ends of the waveguide. We have learned previously that for the TE modes, we can have TE M0 or TE 0N modes in the rectangular waveguide. And then for TM modes, we can have TEMN. M has to be greater than 0. N has to be greater than 0. There's no TM00 mode. Okay. This mode is not there. And that is something that we have gone through previously to convince you that for a rectangular waveguide, those are the possible modes you could have. And if you want to think of this as a TM or TE modes bouncing back and forth, your M and N could only have a certain integer values. for the case of TM wave bouncing back and forth, both M and N has to be larger than 0. For TE modes, one of them can be 0, but not both of them. When both of them are 0, then you have no solution. So, but the question I'm going to ask is it possible that we can have beta Z equal to 0 in this solution? Which means that I can have this term being 0, and yet this term not being 0. It turns out that this is possible when you have TM modes. When your TM modes means that, sorry, is this TM or TE? It should be, yeah. It's TE modes, and TE you can have M and P. You can have P equal to 0, because in that case, what happens then is that you can have TE M and 0 mode possible. And if you can think of this mode, it's a mode with beta Z being 0, which means that this mode has no Z variation. Beta Z is equal to 0 when P equal to 0, because if you recall previously, P equal to 0 means that beta Z equal to 0. This term will go to 0. That means that the wave is not changing in the Z direction. And it turns out that this is possible when you have the TEMN0 mode. And when you have the TEMN0 mode, the magnetic field, okay, Hz is not 0. Okay, when you have this mode, Hz is not 0. When Hz is not 0, and at the same time, because P is equal to 0 implies that there's no Z variation in the field. So this magnetic field would look something like this. Okay, the H field inside the waveguide would look something like this. And what happens is that this is a mode that is possible if this is open. And this is open in this waveguide, which means that the wave is, if I look at the transverse view, okay, if I look at the transverse view, the magnetic fields are coming out of the waveguide. This is the side view, or the magnetic field is going into the waveguide, and then the wave is just bouncing back and forth like this. Okay, it's just bouncing back and forth using the 4 walls of the rectangular waveguide. So it's still possible to have this mode. Okay, that's what I call the KZ equal to 0 case, or the beta Z equal to 0 case. And this will be the TEMN mode. Okay. Okay, so what is the lowest mode of a rectangular cavity? It turns out that that lowest mode is possible if you look at these equations. If you look at these equations again, okay, and if you look at the mode with the lowest resonant frequency, and if you assume that A is larger than B is larger than D, okay, if you assume that this is the case, then the lowest mode is the mode with, well, I have to make one qualification. The resonant frequencies that I have derived here is for an open circuit on this end. If I were to have a short circuit on both ends, then this just becomes P pi. Okay, this will just become P pi, where P is an integer. Okay, you can go through that thinking quite easily. Okay, so when we have open circuit at both ends, then the resonance condition is omega square mu epsilon, which is beta square, is equal to P pi over D, square plus m pi over a square plus n pi over b square. That is the resonance condition. Sorry, it should be short circuit. When we have short circuit at both ends, then that should be the resonance condition, because we went through this process in the beginning saying that if we have short circuits, which is the first example over here, then this becomes a 1, because when you have a short circuit, this is -1, this is -1. This equation becomes that. And the resonance condition is that beta ZD is n pi, where n becomes an integer, but I'm taking n to be p in this problem, okay? So if I have short circuits at both ends, then this is the resonance condition for that cavity. And then if I assume that A is larger than B is larger than D, and D being the smallest one, which means that if I look at this cavity, it will look something like this. If I were to draw a picture of it, it will look something like this, okay? And A is this dimension, B is this dimension, Z is coming out of the paper. And if we make this into a cavity, resonator cavity, by making D the smallest dimension of A, B, and D, and then we short this cavity with a short circuit at this end and a short circuit at this end, then this will correspond to this equation that we have in the beginning, where we had the case where we put a shorted termination at both ends. We will have this set of equations over here. And then the mode will look like this. Okay, this would be the case where P equal to 0, M is equal to 1, N is equal to 1. So the mode that is bouncing back and forth is the TM11 mode. The mode that is propagating back and forth is the TM11 mode, where EZ is not 0 because it's a TM mode, but HZ equal to 0. You can see the picture of this mode. And those modes are looking like this. And then if you make the fact that P has to be 0 by choosing the solution where P is a constant, then the field will look something like this. And you can convince yourself that if you were to look at this resonant frequency, and if D is the smallest of the 3 numbers, you would like to make P equal to 0. Okay, if D is the smallest, because if D is the smallest, this factor pi over D becomes the largest number. And to find the lowest resonant frequency, you would like to pick P equal to 0. And then the other modes that are possible is the PM modes and 110 mode. And can you try TE? You can, if it's TE, it has to be 1s and 0s, okay? And then you do not know what the third integer is. And then of course, if it's TE, you can actually easily convince yourself that the third integer has to be non-zero, okay? So it will have to be something like this. But it turns out that this mode has a higher resonant frequency compared to this one. So this one is the lowest. Okay, that one is the lowest resonant frequency. Are there any questions so far regarding this cavity modes and how you find them? So you can use the same kind of idea for a circular waveguide. And you can convert this circular waveguide into a transmission line model. And then depending on whether you have short circuit or open circuit at the other end, you will find the transverse resonance condition for this rectangle or circular cavity waveguide and find the resonance condition from using this formula. 1 equal to gamma S gamma L e to the minus 2j beta z d. Okay, you go back and find the resonance condition. Of course, beta z is not easy to find for a circular waveguide. It will be given by beta square minus beta s square. And beta s square is not easy to find because those are found by finding the zeros of the Bessel function or the zeros of the derivative of the Bessel functions. And once you have found your beta s that way, you can plug it in here to find your beta z. And then you have to, of course, impose the boundary condition that depending on whether you have short circuit or open circuit terminated, beta zd is p pi, where p is an integer, or beta zd is p pi over 2, where p is an odd integer. Okay, depending on what kind of modes you're looking for there. So you can actually do very interesting stuff with cavity resonators. One example here is you can make it into an antenna. Say if you have a rectangular cavity, if this thing starts to resonate, it means that you can make the field inside the cavity to be very strong. And when the cavity has very strong field inside, and if you open a small aperture on this side, there will be lots of radiation coming out of this cavity. This is the same notion that if you have an LC tank circuit, at the resonant frequency of the LC tank circuit, the currents become very strong. Okay, the currents that slosh back and forth becomes very strong. And by the same token, at the resonance frequency of this cavity, the electromagnetic field inside becomes very strong. And this antenna hence becomes a good radiator at the resonance frequency of this cavity. You can also make filters. Okay, you can also make filters as been shown by this thing here. And before you make filters, we can actually think about how we make filters in circuit theory. You might have come across that before, and I show you the design of a very simple filter at the very beginning. Okay, this is a design of a very simple filter. So you can make filters by using resonators, very much like what you did in circuit theory. For instance, and this would be a very, very simple filter. It's called a one-pole filter. That is, if you have a voltage input here, and then you have a voltage output there, you can see that at the resonant frequency of the resonator, you have the maximum voltage transfer between input and output. This is narrow band, and if you were to find a transfer function, the transfer function will look something like this, where this is the resonant frequency of the resonator. Okay, if you look for the transfer functions of this circuit, it looks something like this. And you can make, for instance, concatenation of resonators. For instance, and then you can have VI, V out. And this might have resonance frequency of omega 1. This one might have resonance frequencies of omega 2. And this one might have resonance frequencies of omega 3. So together they will work to make a three-pole filter. This might be omega 1, this might be omega 2, this might be omega 3, and the transfer function will look something like this. Okay, so you get the idea. With the concatenation of a whole bunch of resonators, you can design filters. And this can also be used in microwave engineering in the sense that if I make a resonator out of a microstrip line, if I can concatenate them, I can make good resonators. And here is an example where I actually use fringing fields to couple two resonators together. So this is one resonator, this is another resonator. But between them, I can put coupling capacitance to account for the fact that this resonator can transfer its energy to the other resonator by capacitive coupling. And here are other designs of resonators. This is like optical illusion, okay? It will take you to adjust your brain to see what is what this picture is, because I find that I have to adjust my brain. Okay, so what you have is that I hope you can see it, because optically we can see this picture two ways. With this been extruded out, or when this been impressed or depressed or extruded in. So I hope you can see that. But essentially, what you have is that you have a microstrip resonator here. You have another microstrip resonator here, and you can concatenate them to make them into a broadband filter. Another way of seeing it is that, well, you might have a concatenation of resonators using microstrip lines, and then you use capacitive coupling between them to couple the energy from one section to another one. And if this capacitive coupling is not strong enough, you can overlap this region and make the overlap region bigger like this one. You can have more coupling. And if that capacitive coupling is still not strong enough, you can make what is called interdigital capacitance. And this will give you more capacitive coupling between the two lines. Then you can have the different kinds of resonators, okay? So you can make all kinds of things. You can make Fabry-Perot resonators, which is also a good kind of optical filter. You can also make microwave sources using coupling between different sources. I will describe that more in the lecture notes. Heuristically, okay, you can also make laser cavity out of a resonator. And then you can have semiconductor lasers that works at room temperature. And so cavity actually has been used everywhere. It can be used as a frequency sensor, okay? And what you do is that you feed microwave energy into this resonator, and it's actually described in this manner. And when you hit the resonant frequency of the cavity will take energy away from the microwave sources, and then you can detect that there's a siphoning of energy away from your system, and that is the resonant frequency of the cavity, okay? Are there any questions before I stop? Any questions, anybody? If not, then I'll let you go then. Okay, and take good care of yourself. And I'll write this out in gory detail in the lecture notes so that you have more time to read them. They're actually quite interesting. And some of you were lamenting the fact that we don't have enough application examples. So here are some real world applications, but those problems cannot be solved in closed form. But we can use our heuristic understanding of them by studying closed form solutions. Okay, that would be the philosophy of microwave engineering. We study closed form solutions to get physical insight. And with that physical insight, we can use them to design complicated microwave systems. Okay, I'll stop here and let you go. And thank you for coming. Okay, bye-bye.